All right, so thank you very much. Is this working? Do I need the microphone? Can I forego the microphone? Is that all right? All right, cool. All right, well, thank you very much for coming, and I'd like to thank the organizers especially very much for this. It's been a wonderful conference, and it's great to be in Korea. I'm going to be talking about, so everything I'll be talking about is joint work with Hans Christian Herbig, and I'll also be talking about some joint work with Carla Farsi, Daniel Herden, and Gerald Schwartz. So for the setup, if we have a unitary representation of a compact Lie group, and for most of the talk, the Lie group will be a torus, but I'll say a couple things about the more general case. So we have the standard definition of the moment map, which is homogeneous quadratic, and we're interested in looking at singular reduction at the zero level of the moment map. So this is their singular symplectic reduction, because zero is a singular value of the moment map, and so the preimage z of zero via the moment map is a singular real algebraic G variety, and the space that we're interested in studying is the quotient, so the standard symplectic quotient of z mod the action of G. So just since we will be mostly interested in the case of a torus representation, that will be described by a weight matrix. So it's pretty standard for the representation, but an L by N weight matrix where L is the dimension of the torus and the action is given this way. And the moment map in this case is given by the following formula. So we have L quadratic polynomials, and the coefficients are the weights of the representation. So the spaces that we're looking at are not smooth manifolds. We're taking the quotient of the singular object by a torus, but they do have a lot of structure. So they inherit a canonical algebra of smooth functions, which we can define to be the G invariant smooth functions on the representation, mod the vanishing, or the G invariant part of the vanishing ideal of the zero fiber of the moment map of Z. And as well, they have an algebra of regular functions that inherits a grading. So we let R of M0 denote the real regular functions, which is same construction but restricting to polynomial functions. Both of these algebras have a Poisson bracket, so the regular functions are a Poisson subalgebra of the smooth functions. And as all of this structure together by a result of Shamar and Lerman makes this into a symplectic stratified space. So it's stratified into smooth manifolds, and each of those smooth manifolds, the smooth structure coincides with the smooth structure of the total space by pulling back via the inclusion, and they all inherit symplectic forms. So in addition, if we choose a generating set for the algebra of invariant functions, or invariant polynomials, we get an embedding of the full quotient V mod G into RK. This is called the Hilbert embedding, and restricting that to the symplectic quotient realizes it as a semi-algebraic set, and by a result of Schwartz and Mather, the smooth quotient that we get as a subset of RK, so from the semi-algebraic structure, it coincides with the smooth structure that we get from invariant functions. So we are interested in which of these are orbifolds, and so to be careful about this, none of them are actually orbifolds, right? Because zero is always fixed by the entire group. So we always have a singular object that has at least one point with infinite isotropy. However, it's known that there are some cases that in terms of the structures that we've described are indistinguishable from symplectic orbifolds. So as an example of this, this is an example due to Cushman-Shamar. I think it's helpful to kind of go over the construction just to see how this works. If we look at the standard action of the torus the action of the circle on CT with weight matrix -1, 1, then just to get an idea, the zero fiber of the moment map Z is given by this equation, and so it's homeomorphic to a cone on the two torus. And if we look at the invariance of this action, and I'll just mention that, so when we're talking about the real invariance, we can compute these in terms of the complex invariance in the usual way, but we look at the representation sum its dual. So in other words, the weight matrix gets extended to that, and we get 4 quadratic invariant polynomials. And if looking at the moment map, the ideal of the moment map, which turns out to be a radical ideal, so we only have to worry about one polynomial p1 minus p2. So essentially, the algebra of regular functions for this quotient is the same thing as taking this algebra, setting p1 equal to p2, so we get 3 quadratic generators with one relation, p1 squared is equal to p3 times p4. Now, this algebra is exactly the same as the real invariance of just the complex numbers with the standard action of z2 just acting by -1. And so we get an isomorphism, which turns out to be a Poisson isomorphism between the Poisson algebras, between this symplectic quotient and the orbifold C mod Z2. And I'll just mention there's a little bit of work to do, but this ring isomorphism actually, so the inequalities of the two spaces correspond. And so this corresponds to a homeomorphism between the two spaces, which when you have this ring isomorphism, you can lift it to an isomorphism of the algebras of smooth functions. So as a symplectic stratified space with smooth structure and all of the other structures that we've talked about, this space is completely indistinguishable from C mod Z2, so from that orbifold. And the question that's motivating this project is to try and understand exactly when this happens. So is this a frequent thing? It's ideally we'd like to take a representation of a compact Lie group and be able to tell right from the representation whether or not it's somehow isomorphic to a linear symplectic quotient. And, yes?
How do you define symplectic function on C mod Z2?
It's defined in exactly the same way, except for a finite group, the same way as a symplectic quotient, except for a finite group, the moment map is trivial. So we don't have to mod out by an ideal. So in other words, it's the smooth functions that are invariant under the Z2 action. Smooth functions on C.
On C and invariant.
Yes, exactly. Yeah, and by the Schwartz-Mather theorem, again, this is essentially generated by the invariant polynomials. Okay, so we want to know when this happens, and just to give some language for this, when I say linear symplectic orbifold, I mean CK mod a finite subgroup of the unitary group. And so this is kind of a local question. The abstractions to this are local, so we're just looking at representations, but by the symplectic slice theorem, you can do the same for singular symplectic quotients of manifolds. So for a diffeomorphism between such spaces will mean a homeomorphism that induces an isomorphism on the algebras of smooth functions. For a symplectomorphism, we mean that isomorphism also is a Poisson isomorphism, so it preserves the Poisson bracket. And if the diffeo or symplectomorphism restricts to an isomorphism on the regular functions, we'll call it regular. That preserves the grading, we'll call it graded regular. So these are all different kinds of isomorphism. And so a graded regular symplectomorphism will be the strongest equivalence that we can get. And I'll mention that we're really interested in whether or not symplectomorphisms exist, but all of the symplectomorphisms that we know are constructed from regular symplectomorphisms. So the polynomials are much more tractable. We won't be too interested in the Poisson structure, except that by a result of Schmar and Lehrman, the Poisson algebra of smooth functions determines the stratification. So I haven't mentioned that the stratifications have to coincide, and the reason for this is that if there's a symplectomorphism, then that implies that the homeomorphism preserves symplectic strata. Okay, so the first result, and this is a result with Karl Farsi and Hans Christian Herbig, is that there are a lot of orbifold cases. So looking at torus actions, if we take a weight matrix that's of this form, where the diagonal part, these are all negative entries, and then on the right side, these are all non-negative entries, and they're at most one of them is non-zero in each row, then we will always get something that is graded regularly symplectomorphic to an orbifold. So these are all orbifold cases, and this is kind of the kind of result that we were hoping for, is that you can compute exactly what orbifold you're talking about directly from the weights of the representation. So you get a product of C mod a cyclic group, and the order of the cyclic group can be computed from the weights of the representation. And I'll mention that the proof of this is a direct computation. These cases are simple enough so that you can compute the invariant polynomials and the ideal that defines the zero fiber of the limit map, and so you can explicitly compute the graded regular symplectomorphism in these cases. Now, probably a lot of us are thinking that this is somehow related to a toric variety associated to this weight matrix. And so I'll just recall the Kemp Ness homeomorphism. So since these are unitary representations, we can complexify the group, and that extends to a representation of the complexified group on the same representation space. And by the Kemp Ness theorem, the inclusion of the zero fiber into the moment map, or of the moment map into the representation, induces a homeomorphism between the symplectic quotient and the GIT quotient of the resulting representation, right? So in other words, and in the language of the Kemp Ness homeomorphism, this would be said that the zero fiber of the moment map is a Kemp Ness set. And so let me give one definition that will just allow me to simply state some hypotheses going forward. When we complexify the representation, we say that it's stable if it contains an open dense subset consisting of closed orbits. So when you take the GIT quotient, you throw away all the orbits that aren't closed. And just as an example, the T1 representation just given by 1, 1 by these weights, so just the diagonal action is not stable. And in this case, the zero fiber of the moment map is a point. So this is why we want to throw these kinds of things out. Representations that fail to be stable, in some sense you're looking at the wrong representation from the perspective of the symplectic quotient. You can always exchange this with a smaller representation, in this case, the trivial group on a point, to understand it better. And so this is just, we want to ignore these without loss of generality for the sake of simplicity.
Can I ask a question? So
Yes.
The function is a point, but you are the definition of the functions.
Yes.
It's not trivial.
Yes, and that is, well, it depends on which definition that you pick. So there is a notion of what the regular functions associated to this point would be. But again, so for the smooth functions, it definitely would just be a point, and so it would be trivial. And so since we're interested in the smooth function at the end of the day, we're going to want to consider this a point and kind of ignore what the non-trivial regular functions might be. Thanks. Okay, so the next result is a result that shows a lot of non-orbifold cases. And so the idea here is still, in the case of a torus, we have a faithful and stable representation with trivial fixed points, so just fixing the origin. And then the symplectic quotient in this case will be a rational homology manifold if and only if by permuting the rows and, permuting the columns and doing row reduction over Z, you can put it in the form DC, where D is a diagonal matrix with strictly negative entries and C has non-negative entries. The reason for this is that in this case, the GIT quotients are affine toric varieties. So by the Kemp Ness homeomorphism, the topology of this is determined by some toric variety. And the condition that we put on the weight matrix is equivalent to the cone of that toric variety being simplicial. So that if this is the case, then we get a toric orbifold. So we know that it's homeomorphic to an orbifold. Interestingly enough, if it's symplectomorphic to an orbifold, it will be a different orbifold. So we get homeomorphisms, but they're not smooth, and they don't preserve the groups that we're talking about. So in the example of 1, -1, we got the orbifold C mod Z2. The toric variety is smooth. It's C in that case. All right, and so symplectic orbifolds are always rational homology manifolds. So this gives us a criteria for something that we can see this as the symplectic quotient is homeomorphic to some symplectic orbifold if and only if this condition is satisfied. And as well, it gives us a lot of non-orbifold examples. So we have some orbifold examples in the torus case, and we have a lot of non-orbifold examples. So just to name one, the symplectic quotient associated to this weight matrix is not a rational homology manifold, and so it cannot be even homeomorphic to a symplectic orbifold. And I'll just mention that in this case, it's obvious that no matter how you permute the columns and row reduce, you can't can't get all the entries to the right of the diagonal part to be positive. There's an easier criteria in direct computation, so you can just compute the vertices of the cone, or the generators of the cone, directly from that matrix, and from there can determine whether or not it's of the right form. So this, we've now got a lot of non-orbifold and a lot of orbifold cases in gray area in between, and to try and fill in that gray area, I want to look at restrict to the case of a circle action. So we're letting L be equal to 1, and then we have a weight vector. In this case, I'll just mention the stability condition is just equivalent to there have to be both positive and negative weights. And if you remember the form of the moment map, these are coefficients of sums of moduli. So if all the weights are positive or all the weights are negative, then the symplectic quotient is a point, because it's just the origin satisfies that. And if we assume stability, then in this case, the symplectic quotient will be a rational homology manifold if and only if exactly one weight is negative, up to row reducing, which in this case means one weight is negative and the rest are positive, or one weight is positive and the rest are negative. So these are the unknown cases here. And so I want to talk about the theorem that if the dimension of the representation is greater than or equal to 3, so if n is 3 or more, then we will not get an orbifold. So we can show that M0 is not graded regularly symplectomorphic to a linear orbifold. And this gives a complete answer for the case of circle actions, because all of the dimension, 1 and 2 cases were addressed by the theorem that shows that they're explicitly orbifolds. So in this case, the dimension essentially determines whether or not you get an orbifold. So that's the corollary stated here. To talk about the proof of this theorem, I want to digress a little bit and talk about a way of understanding the grading. So recall that if you have a finitely generated graded algebra, the Hilbert series is essentially just counts the dimension of each of the graded pieces. So it's a formal power series where each of the coefficients is the dimension of the vector space of pieces of grade k. And this is always going to be the power series of a rational function with a pole at x equals 1. And already the pole order tells you the Krull dimension of the algebra. So there's geometric information in the Hilbert series. And in particular, if you look at the Laurent expansion at x equals 1, then you get a Laurent expansion that looks like this. Again, the Krull dimension shows you the pole order. And the coefficients gamma k of this Laurent expansion contain a lot of information about the geometry associated to the algebra. So first, to illustrate this, let me just point out that if we're looking at complex invariance, so kind of the standard classical invariant theory, the first Laurent expansion, and this is of a finite group, gamma. So finite unitary representation of gamma acting on some Cn. The first Laurent coefficient gives you 1 over the order of the group. And the second one essentially determines the number of pseudo-reflections in the group, where a pseudo-reflection, a group element that fixes a hyperplane, right? So we see some geometric information here. Now we're interested in the real invariance. And the real invariance, they have the same Hilbert series as if you take the representation, product it with its dual, essentially in coordinates z and z bar. And so what we get is gamma 0 is still 1 over the order of the group. Gamma 1 is equal to 0, because from the real perspective, there are no pseudo-reflections, right? And then gamma 2 is always equal to gamma 3. And it essentially counts the pseudo-reflections of the complex representation. So things that, from the real perspective, fix something of codimension 2. And I'll mention it doesn't just count them. In some sense, it counts their orders. So you take an order of a nice generating set of pseudo-reflections and sum up the squares of their orders minus 1, and that tells you gamma 2 and gamma 3. So these are the Laurent coefficients of the Hilbert series for a real finite group, so for a real orbifold. And so the idea was we can try and compute the Laurent coefficients for the Hilbert series of a symplectic circle quotient and compare them to these. So we have a result that gives the Laurent coefficients. So gamma 0, and I'll just say, so again, we have a weight vector a1 through an. because of exactly what you were mentioning, the signs don't matter, right? Because the signs were important for the topology, but in some sense for the regular functions, even if it's a point, it doesn't matter. So essentially, I'm just going to let alpha be the absolute values of the weights because we can throw those out. And then gamma 0 is given by a quotient of Schur polynomials in the weights. So a quotient of some symmetric polynomials in the absolute values of the weights. Gamma 1 is equal to 0. Gamma 2 and gamma 3 are the same, and you can compute them in terms of the weights. So again, Schur polynomials, so quotients of symmetric polynomials in the weights, and the GCDs of sort of the codimension 1 strata show up in here. So that's what the sum down there is doing. So to give this in a little bit more of a tractable way, if all of the weights are distinct, and I just let alphas be the absolute values for simplicity, gamma 0 looks like this. Gamma 2 and gamma 3, we have formulas that look like these. And I'll mention that this is a tedious but relatively direct computation. The hard part is showing that, so there are the singularities that correspond when alpha I is equal to alpha j, so when two weights coincide, those are removable singularities. And showing that even when two weights coincide, taking out those removable singularities gives you the same formula was kind of the hard part in this computation. But anyway, so nonetheless, and I think I also have, for n equals 3, just to give even more tractable examples, these are what the coefficients look like in terms of the 3 weights of the representation. So nice ratios of symmetric polynomials. So we were talking about this in order to prove that the Hilbert series of an orbifold and the Hilbert series of a symplectic quotient are not the same. The way this proof works is essentially you assume that you have a symplectic quotient that's graded regularly symplectomorphic to an orbifold. And then because gamma 2 is greater than 0, so you can show from the formulas for gamma 2 for a symplectic quotient, gamma 2 is greater than 0, which means that for the orbifold, the gamma 2 must be greater than 0. So remember, this was associated to pseudoreflections. That means that there must be a pseudoreflection in the orbifold that we're talking about. So this orbifold has to have a codimension, so a real codimension 2 stratum, since it's a complex pseudoreflection. Well, for torus symplectic quotients, they're fairly simple. The stratification is fairly simple. The strata, or the closures of the strata, are symplectic quotients of lower dimensional circle representations. And so what you can do is, with a little bit of work, show that you must also have the closure of this strata is also graded regularly symplectomorphic to a suborbifold of the other orbifold. After a while, you reduce down to the case that n is equal to 3. And then the fun part is that all of the finite subgroups of U2, so all of the possible gamma when n is equal to 3 that could represent this orbifold, have been classified by Duval. I think the best, so the best exposition of this is in Coxeter's book. And there are 9 families, and you can go through and for each family argue that there are inconsistencies with the Hilbert series of a symplectic quotient. So it's very brute force, and it's not what we were hoping when we sat down to do this. In some sense, it's an inductive proof where the inductive step is a page and the base case is 9 or something like that. So brute force, not elegant mathematics. But the reason for that is that we were actually hoping that the gamma I for symplectic quotients and orbifolds would have some very different, some distinct differences when we sat down to do this. But one thing that I've been kind of color highlighting with all these is that in both of them we see the same relations. Gamma 1 was always equal to 0, whether it's a symplectic quotient or an orbifold. Gamma 2 minus gamma 3 was always equal to 0. And this keeps going, actually. Gamma 3 minus 2 gamma 4 plus gamma 5 is equal to 0. And in general, if you start at any level in the Laurent coefficients for either an orbifold or a circle symplectic quotient, and you take so you start at the m minus first level and the mth level, and you sum up the next m coefficients, alternating sum with binomial coefficients as the coefficients, you always get 0. So these are relations that were satisfied by orbifolds, and experimentally we were seeing they were satisfied by all circle quotients. And this, I don't know, spent a long time fussing with these relations before we realized what they mean, and I think they're very pretty relations between these coefficients. But it turns out that they are related to the following fact. So if you have a Noetherian graded Cohen-Macaulay domain, then by a result of Stanley, it is Gorenstein if and only if the Hilbert series satisfies this functional equation. And with these two coefficients, I'll mention that, so it's called graded Gorenstein, or totally Gorenstein, or completely Gorenstein, if the two exponents are the same. So the Krull dimension is equal to the so-called A invariant. And this is equivalent to these relations among the Laurent coefficients. So this is in joint work with Hans Christian Herbig and Daniel Herden. We were able to see that this functional equation implies these things that we were seeing. So it's a theorem of Watanabe, or a consequence of it, that the real invariants of a symplectic orbifold are always going to be graded Gorenstein. But as well, we can prove that for any torus representation, the corresponding symplectic quotient is graded Gorenstein as well. So in other words, the property of graded Gorensteinness is shared by symplectic quotients, by all torus symplectic quotients, and by orbifolds. And this is one of the things that we're seeing. There are a lot of experimental computations in what we're doing, and the theme of what we're finding is that it seems like even though there aren't a lot of orbifold singular symplectic quotients, the nice ring theoretic properties that orbifolds have are shared by all symplectic quotients. And I'll mention that we don't have a lot of results in the non-abelian case, but experimentally everything that we've checked satisfies these relations as well. So I'm not going to state a conjecture, but maybe they're all graded Gorenstein, or at least generically graded Gorenstein somehow. All right, and yeah, so just to finish off, let me mention that this has been kind of a result of a fixation with the grading of these algebras, right? And so recently we've been working with Jerry Schwartz and working on kind of ignoring the grading and trying to find results related to the smooth functions or the regular functions. So it's what we're seeing with this is that if you look at the grading, orbifolds and non-orbifolds, except for ad hoc methods, seem to be somewhat indistinguishable. So I will just very quickly state two results that we've been able to get just ignoring the grading and looking more generally. And one is that using kind of more GIT methods on the complexifications of these quotients, we've been able to strengthen this theorem for circle action. So the previous theorem was identical to this, except we said graded regularly symplectomorphic. And it turns out that for circle quotients, either they are orbifolds or they do not even admit a regular diffeomorphism to a linear orbifold. And for the next quotient, or excuse me, for the last result, let me just mention that, so for a representation of a complex reductive group, we say that it's two principal if you take the initial representation and remove all of the points that do not project down to a principal orbit, and you're left with, you've removed a set of complex codimension 2 or more. And I'll say two principal, this condition is somewhat generic. So for many groups, all but finitely many representations are two principal, and we've been able to show that if the complexification of the action is two principal, then the symplectic quotient is not an orbifold, and in this case, we can ignore the regular functions. It's not symplectomorphic to any linear orbifold. So just to go back and close on tori, again, I'll say this is an example of a two torus action that is, the symplectic quotient is a rational homology manifold. So it was in the gray area earlier of not sure what whether or not it was an orbifold, but the action is two principal when you complexify. So this is an example of something that's now determined to be a non-orbifold. So thank you all very much. I appreciate your attention.